What does a data center look like? The answer depends on who you are. For example, to the public, a data center looks like this. To the installation personnel, a data center looks like this. To the IT engineers, a data center may look like this. To the network engineers, a data center looks like this. Now, let's look at a data center from the perspective of network engineers. Network engineers focus on the data center network when they look at a data center. So, what is a data center network? A data center network is part of the infrastructure in a data center. The network connects enterprise customers to computing, storage, and other resources. The data center network consists of the computing network, storage network, and data center interconnection network. The computing network is the core network in a data center and connects users to computing resources such as servers. Unless otherwise specified, the data center network mentioned in this video refers to the computing network. Similar to campus networks, most traditional data center networks use a layer 2 and layer 3 mixed network architecture. This network architecture is used because it is very mature. Mature layer 2 and layer 3 network technologies, such as spanning tree protocol and routing, can be easily deployed on the network and are applicable to zone-based and modular services in the data center. However, as traditional data centers evolved virtualized data centers and cloud-based data centers, this network architecture gradually cannot meet increasing requirements. Why? The reason is virtualized and cloud-based data centers use a key technology, server virtualization. This technology virtualizes a physical server into multiple logical servers called virtual machines. Each VM runs independently and has its own OS, apps, MAC address, and IP address. Server virtualization effectively improves server utilization, ensures on-demand service and resource provision, reduces energy consumption, and lowers customer operation and maintenance costs. Server virtualization is widely used. After servers are virtualized, the demand for dynamic VM migration emerges. Dynamic VM migration refers to the process of migrating one VM from one physical server to another physical server when ensuring the VM runs properly. End users are unaware of this process. Dynamic VM migration allows the administrator to flexibly adjust and allocate server resources, or maintain and upgrade physical servers without affecting user services. The key of dynamic VM migration is services on VMs cannot be interrupted during VM migration. This requires IP addresses and VM running status such as the TCP session status to remain unchanged. VMs can only be dynamically migrated in the same layer 2 domain, but not across layer 2 domains. In the previously mentioned architecture of traditional data centers, redundant devices and links are to be deployed at layer 2 to improve reliability. Physical loops occur. Loop prevention protocols such as STP are to be configured to block redundant links and prevent broadcast storms caused by loops. Due to performance limitations of STP, an STP-enabled layer 2 network generally contains a maximum of 50 network nodes. Dynamic VM migration can only be performed within a small area and is restricted. Dynamic VM migration in a large area or even cross areas requires all servers involved to be included in the same layer 2 network domain to form a large layer 2 network. VMs then can be migrated to a large area smoothly. This large layer 2 network that facilitates VM migration in a large area anytime, anywhere, is called a large layer 2 network. As mentioned above, a large layer 2 network cannot be constructed using STP. New technologies are required. Currently, large layer 2 networks are constructed using the following types of technologies, with various principles and application scenarios. Network device virtualization technologies are of the first type. These technologies virtualize 2 or more physical network devices working in redundancy mode into a logical network device that only functions as one node on the entire network. Network device virtualization technologies work with link aggregation technologies to change the original multi-node and multi-link physical structure into a single node and single link logical structure that prevents loops. No loop prevention protocol is required. The Layer 2 network scale is not limited by loop prevention protocols, and large Layer 2 networks can be constructed. Major network device virtualization technologies include the cluster switch system for modular switches, intelligent stacking for fixed switches, and super virtual fabric for mixed stacking of modular and fixed switches, as well as stacking of fixed switches. Large Layer 2 networks constructed using network device virtualization technologies feature simple, logical network structure and easy management and maintenance. The scale of such networks is smaller than that of large Layer 2 networks constructed using other technologies. Network device virtualization technologies are proprietary technologies of different vendors. If one of these technologies is used to construct a large Layer 2 network, only devices from the same vendor can be deployed on the network. These technologies are suitable for constructing large Layer 2 networks with small and medium-sized points of delivery. Routing Layer 2 forwarding technologies, such as transparent interconnection of lots of links and shortest path bridging, are the second type of technologies for constructing large Layer 2 networks. These technologies also focus on loop prevention. These technologies do not block redundant links like STP or prevent loops like network device virtualization technologies. They borrow the logical loop prevention mode from Layer 3 networks. How are loops prevented on Layer 3 networks? As mentioned above, redundant links on Layer 2 networks are to be blocked to prevent loops. Layer 3 networks also have loops. Why are redundant links not blocked? The reason is Layer 3 networks using routing protocols to collect, synchronize, and update the network topology so that every network node can identify the best forwarding path. Packets do not loop on forwarding paths even though physical loops occur, ensuring logical loops are prevented. Routing Layer 2 forwarding technologies are based on this idea and introduce Layer 3 route-based forwarding mechanism to Layer 2 networks to remove loops. Traditional Layer 2 loop prevention protocols such as STP are not required, and large Layer 2 networks can be constructed. Take TRILL for an example. It adds a TRILL frame header to an Ethernet frame and encapsulates the frame in a new external Ethernet frame to implement transparent transmission of the original Ethernet frame. TRILL-enabled switches can forward the frame based on the nickname in the TRILL frame header. Nicknames are similar to routes and can be collected, synchronized, and updated using ISIS. When VMs are migrated on a TRILL network, ISIS automatically updates the forwarding table on each switch, ensuring IP addresses and other states of the VMs remain unchanged so VMs can be dynamically migrated. The scale of large Layer 2 networks constructed using TRILL is larger. TRILL is a standard IETF protocol and facilitates interoperability between devices from different vendors. TRILL is suitable for constructing large Layer 2 networks in a large POD or data center. However, TRILL is a new technology. TRILL deployment requires new software and hardware devices. The investment costs are high. Network device virtualization and routing Layer 2 forwarding technologies are large Layer 2 technologies proposed and dominated by network device vendors. Technologies of the third type are proposed by IT vendors. These technologies are overlay technologies, such as virtual extensible LAN and network virtualization using generic routing encapsulation. Overlay technologies use tunnel encapsulation and decapsulation. These technologies encapsulate original Layer 2 packets sent by a source host, transparently transmit the packets on the existing bearer network, decapsulate the packets on the destination, and forward the decapsulated packets to the destination host. The source and destination hosts then can communicate at Layer 2. These technologies use tunnel encapsulation and decapsulation to overlay a large Layer 2 network on a bearer network. These technologies are called overlay technologies. Overlay technologies virtualize the entire bearer network into a super large Layer 2 switch. Each VM directly connects to a port of this switch. No loop occurs. During dynamic VM migration, a VM is migrated from one port to another port, and its status remains unchanged. IT vendors propose overlay solutions such as VXLAN from VMware and NVGRE from Microsoft. The reason IT vendors propose such solutions is that they want to end technical dependency on network device vendors and independently construct large Layer 2 networks. In overlay solutions, the bearer network only needs to provide basic switching and forwarding capabilities. Encapsulation and decapsulation of original packets are performed by VMs on servers and do not depend on network devices. Take VXLAN as an example. VXLAN uses the MAC in UDP encapsulation mode. A virtual switch adds a VXLAN frame header to a Layer 2 data packet sent by a VM, adds a UDP header to the packet, and encapsulates the packet in an IP header and an Ethernet frame based on IP addresses and MAC addresses on the bearer network. The bearer network only needs to forward the packets based on common layer 2 and layer 3 forwarding processes. Overlay technologies do not depend on the bearer network and fully use the existing basic network to construct a large layer 2 network. They also have obvious advantages in support for SDN and multi-tenant. Overlay technologies are the hottest large layer 2 network technologies and can construct large layer 2 networks for a data center or across data centers. Constructing a large layer 2 network involves two control planes of the overlay network and underlay network. Network management, maintenance, and fault location become more complex. Operation and maintenance workload is more heavy. The last type is Ethernet virtual network technology. EVN is not for constructing a large layer 2 network in a data center, but is for implementing cross-data center layer 2 interconnection. Traditional technologies for layer 2 interconnection between data centers include virtual private LAN services and enhanced VPLS over GRE. These technologies have problems such as complex configuration, low bandwidth utilization, high network deployment costs, and high network resource consumption. EVN is a VPN technology based on the VXLAN tunnel for layer 2 interconnection and can be considered as the extension of VXLAN. This technology uses the multi-protocol extensions for Border Gateway Protocol to transmit MAC addresses between layer 2 networks and forward layer 2 packets using the generated MAC address entries. EVN supports functions such as automatic establishment of a VXLAN tunnel, load balancing for multi-homing access, route reflection function of BGP, and ARP cache proxy. It effectively solves problems of VPLS and other layer 2 interconnection technologies, and is one of the ideal solutions for layer 2 interconnection between data centers. This video simply introduces several commonly used technologies on large layer 2 networks. Characteristics and major application scenarios of these technologies are as follows. For more information, visit e.huawei.com.